Hey guys, let's start. So good morning. Today we have Francisca Vasconcelos.
Yes.
All right. From Berkeley, she's a student of, if I read correctly, it's a weird combination, Michael Jordan and Umesh Vazirani. And I also see that the title changed because I was expecting some deep thoughts on neural network. Let's see what we get.
Thanks so much for the invitation to speak today. I'm Francisca Vasconcelos at Berkeley, and today I'll be telling you about a series of work in my PhD on quantum circuit complexity, specifically this QAC0 circuit class that we'll dive into. But before I get started, I just want to acknowledge the many great collaborators I've done this work with, including Ben Foxman at Yale, Robert Huang at Caltech, Shivnath Pali at MIT, Natalie Parham, and Henry Yuan at Columbia. All right, so I modeled my talk today after every great literary story. We're going to follow the standard hero's journey narrative arc, which is typically divided into three main parts. So in the first part or act, we're going to depart from the ordinary world. In this case, moving from classical to quantum circuit complexity. And so here I'll really give some background on the relevant circuit classes in classical complexity, and then we'll describe their quantum analogs. In the second part, our hero will face some crisis and trials. So in particular, we'll discuss QAC0's main identity crisis, which is whether QAC0 is equal to QAC0 with fan-out. This is analogous to a problem that some of you might have heard of in the classical setting, which is whether parity is in the AC0 circuit class. We'll then describe some attempts at trying to resolve this identity crisis, first describing the only known upper bound for this problem, essentially showing that QAC0 with fan-out is equal to QAC0 if we give it exponential power. And I'll define concretely what exactly I mean by power. We'll then go into some of my own work on trying to prove lower bounds for this QAC0 circuit class. And in particular, we'll show a nice structural result, essentially showing that QAC0 with limited power is in fact Fourier concentrated. And then in the final act, the hero will return transformed. And if we have time, we'll kind of go into some discussions about how this work on trying to resolve this big open question could be used to actually show efficient learning of this QAC0 circuit class, as well as implementations of pseudo-randomness and corresponding learning lower bounds for the class. All right, so before I jump into the story, I want to motivate kind of why you might be interested in this QAC0 circuit class. And so for the complexity theorists of this audience, there are a few motivations. The first is that the results I'll present today are essentially quantum analogs of several important classical results in circuit complexity, learning theory, analysis of Boolean functions, and pseudo-randomness. So hopefully they'll be of interest and potentially familiar to many of you. There are also very few techniques that currently exist for proving quantum circuit lower bounds, especially in regimes where gates can act on many qubits simultaneously, which is exactly the regime that QAC0 operates in. Furthermore, there's this big open question that I alluded to before, this question of whether parity and fan-out are in QAC0. At this point, it's almost a 30-year-old open question, and it's deeply intertwined with many of the results I'll discuss today. For a more quantum crowd, there would be some different motivations. So to briefly go through those, we're currently in this noisy intermediate scale quantum era where we only have access to small noisy devices. And realistically, we can only run shallow quantum circuits on these devices, and this QAC0 circuit class is a shallow class. Furthermore, any techniques we develop for understanding QAC0 gives us a novel understanding of entanglement propagation in these quantum circuits, which is pretty exciting. And furthermore, some recent developments in these notions of intermediate measurements actually make QAC0 seem less like a theoretical class of interest, but actually an experimentally feasible one.
Really on many bits?
Yes.
Really on many, like how many?
Oh, I guess there haven't been experimental demonstrations, but this work on intermediate measurements actually takes away the need of implementing like a very wide gate and being able to kind of simulate it through doing kind of more local measurements on smaller subsystems. So it then becomes a bit more practically feasible, because implementing very wide gates is very hard because it requires you to have very fine control over entanglement, which is a bit out of hand for practitioners right now.
This is with our approach. In this experiment, they use our correction or not?
I guess intermediate measurements are the techniques that people are developing to run like quantum error correction techniques. So I guess the recent developments have been showing the connection between these intermediate measurement schemes and the QAC0 circuit model. And then finally, any progress we make on understanding QAC0 leads towards progress in understanding QNC1, which is definitely an experimentally feasible class of now logarithmic instead of just constant depth. All right, so with that, let's get into the main content of the talk. And in particular, I'll start off by giving some background on the relevant classical and quantum circuit complexity. So we're going to start off in the classical realm, and here are two main circuit classes of interest will be NC and AC0. Potentially, many of you have seen these before, but if not, I'll briefly describe them. So the NC's circuit class is essentially the class consisting of layers of alternating ands and or operations. And one of the key things to note about this class is that the gates are constrained to constant width. When we write NC0, we're restricting to gates of constant depth, or circuits of constant depth. And AC is essentially the same thing as NC. The only really key difference in this class is that now our gates, instead of being constant width, can act on an arbitrary number of inputs. Once again, when we write AC0, we're constraining to constant depth. And one final major constraint I should note about both of these circuit classes is actually that the size or total number of gates is constrained to be polynomial in the total number of inputs.
In the NC0 class, you probably want more than one output, otherwise the output won't see many.
I see. Yeah, I guess in this class we'll largely, or in this talk we'll largely be focusing predominantly on AC0. But in the quantum setting, we'll briefly mention some things to do more with NC0, but thank you. Okay, and there were some very exciting work proving structural results on classical AC0, but in order to understand this, I'm just going to give a brief review of classical analysis of Boolean functions for anyone who might not be familiar. And this is what was used to ultimately prove the structural results. But I guess to start off with, the key insight of analysis of Boolean functions is really this observation that parity functions, which operate on subsets of bits, form an orthonormal basis for Boolean functions. And so with this, we can define a notion of a Fourier transform, which looks like this, where our parity functions form an orthonormal basis, and these f hat components are Fourier coefficients. So here's an example of a Boolean function that's only dependent, for example, on the first two inputs. And there's a few other properties I should mention. So first, a very important notion is the notion of degree, which essentially corresponds to the number of input bits that the parity function operates on. We also have this very important theorem, Parseval's theorem, which says that the inner product of two Boolean functions, or the sum of their Fourier coefficient squared, is 1. And this is an important normalization criterion. And then finally, we define the Fourier weight at a specific degree as W equals to K in this case, or we might say greater than K, and that's just the sum of the Fourier coefficient squared at that degree level. And so if you wanted to, for example, have a more visual representation of this, you could, for example, plot the Fourier spectrum of a Boolean function. In this case, I've plotted the Fourier spectrum of the parity function, being parity operating on all n bits, And we see that its Fourier spectrum is concentrated at the maximal degree n.
Just a remark, like the notation there was like S in n, but it's like subsets of n, right? Just
Oh,
Subsets
well,
of
Oh, sorry,
it's
sorry.
all subsets, not
subsets.
yes, sorry.
This is in plus minus one.
yeah, plus minus one, but
Yes, sorry. Thanks for correcting that. And so with this background on analysis of Boolean function, we can now state one of the main results regarding AC0, which was this work by Lignel, Metzler, Nissan in 1993, where they essentially showed that for an AC0 circuit, its Fourier spectrum at degree greater than k decays inversely exponential in the size of the degree. So in terms of this question of whether parity is an AC0 or not, this would imply that for all k, essentially in 0 to n minus 1, you need that the size is greater than 2 to the k 1 over d, which implies that the size needs to be this super polynomial value. However, this is a contradiction since, as we mentioned before, AC0 is constrained to be of size polynomial in the number of inputs. And perhaps a more visual way to really depict what this result is showing, if you were to plot the Fourier spectrum of an arbitrary function implemented in AC0, most of its Fourier mass is concentrated on low degree terms and then decays exponentially as the Fourier degree increases. Meanwhile, if we plot the parity function, as we saw before, it's concentrated at maximal degree. And so if you then try and compute the correlation between these functions computed by AC0 and the parity function, which you might be trying to implement in this class, you can show that they're not very correlated and therefore AC0 can't implement parity. One other important consequence of this result, using this observation that most of the Fourier mass is concentrated on the lower degree terms, is that you actually get an efficient learning algorithm for the AC0 circuit class. When you sample the low degree terms, you can learn it in just quasi-polynomial samples and time. All right, so that's it for my.
explain the last remark, like this. What would I do, like if I want to efficiently learn?
Right, so I guess what you would do is you would have a learning procedure that would sample the Fourier coefficients of the Boolean function that the AC0 class is implementing. And you would try and learn all of these low degree coefficients, and there's only quasi-polynomially many of them. So you can learn each of those to high precision. You'll then learn something that's not exactly a Boolean function, but then you can efficiently do a projection into the space of Boolean functions, and you'll get the guarantee that
It will be quite consistent with my original.
Yeah, but you're not doing proper learning in the sense of learning an actual AC0 circuit, then implementing that function. You're just learning a description in
Fourier space. Yeah.
Yeah.
Okay.
Very good question. Great. So now that we've reviewed the necessary classical background, we'll now move to the quantum realm, where our main circuit classes of interest are the QNC0 and QAC0 circuit classes. Before I describe those circuit classes, I just wanted to do a brief review on some background in quantum mechanics and quantum computation for those who might not be super familiar. So we'll start off by defining the notions of quantum states. And so the first thing we'll do is we'll map the notion of a classical state into the quantum setting. In this case, if you have a classical bit, you denote it 0 or 1 inside these kets. Whenever you see a ket, you should just think of a vector. 0 corresponds to the 1, 0 basis vector, and 1 corresponds to the 0, 1 basis vector. We can then move, for example, to a 2-qubit system, encoding a 2-bit classical state by simply taking the tensor product of those two vectors, and you'll then get a 4-dimensional vector. And then if you keep extending this procedure, when you move to an n-qubit system, you'll have a 2 to the n dimensional vector encoding all of the 2 to the n possible n bit strings. Now, quantum state, when we have exact kind of certainty over the state of our system, is really just a linear combination over these classical basis vectors. And there's a few important things to note. The first is that when we take this linear combination, all of our coefficients can actually be complex, not necessarily real valued numbers. And also that the norm squared, the sum of the norm squared of these coefficients is equal to 1. Now, in the quantum setting, sometimes we have a bit of classical uncertainty over the state of our system, which we can then represent mathematically by basically taking weighted probability distributions of our classical basis states. So when I write this weird symbol here, this is essentially just saying an outer product. When we write the backwards ket, this is just the conjugate transpose of the vector. And so this is really just a matrix, which is a weighted combination of our initial pure state weighted by p sub I. And kind of a key thing to note about these n-qubit mixed states is that they really have 3 key mathematical properties. They're Hermitian matrices, they're positive semi-definite, and they're trace 1. So that's it for defining quantum states. And also, if anyone has a question about anything, feel free to interrupt. I know I'm going a bit fast. Measurement, on the other hand, is a very nuanced topic in quantum mechanics. It's the basis of a lot of these different interpretations of quantum mechanics. So I'll stick to a purely mathematical description here. But we define measurement in the quantum setting with respect to observables, which can essentially be represented at the end of the day by any Hermitian matrix. And we say that the measurement outcome of an experiment with respect to these mixed states, or even in the case of a pure state, we can describe that as like a mixed state just with probability 1 for the pure state of interest. So really the measurement outcome of any experiment is just taken by this trace of the state observable inner product, often referred to as the Hilbert-Schmidt inner product. And one key thing to note is that this is something that you can actually go and measure in the lab, so it's always going to be real valued. And one last kind of subtle thing that I want to mention is this notion of throwing away qubits, which will turn out to be very important in our setting. And so if you have a quantum system which acts on multiple subsets of qubits, you might only be interested in a smaller subset. And so if you want to essentially throw away or ignore or disregard the other subset of qubits, you can use this partial trace operation, which essentially corresponds to, in this case, throwing away all of the qubits which lie in subsystem B of your 2-subsystem state. All right, and so with that, I'll move on to describing quantum computation, which ultimately is really just governed by these quantum gates, which mathematically are simply unitary matrices. When we want to talk about evolution, the evolution of a pure state is given by multiplying this unitary matrix by our state of interest, our pure state. In the mixed state setting, the evolution is actually given by just doing the left-right conjugation of our density matrix. And then a lot of times we'll want to pictorially depict what a quantum circuit is doing. And so this is kind of analogous to when we draw classical circuits. So the way we usually do this depiction is, for example, in this case, we have a 3-qubit system, which is in states Q1, Q2, Q3. We'll then apply our circuit, which is going to propagate in time from left to right. And in this case, we're not doing anything to the first wire. It's just an identity. So this qubit's going to remain unchanged in time. But then we're going to do some non-trivial computation on the last 2 qubits, which will result in then an output state that we can measure. Mathematically, if we were to represent this circuit, it would look something like this. The only key difference really being that time goes left to right in the pictorial sense, but then mathematically we apply our operations right to left. And then one other important thing that I'll note that will be very important in our work on QAC0 is this idea of ancilla, which is essentially an additional workspace that we get in the quantum setting. And I guess intuitively, one reason why we care about this is in the quantum setting, all of our gates, as I mentioned, are unitary or reversible operations. And so this makes our quantum circuits actually perhaps more analogous to classical reversible circuits than the kind of standard circuits that you might see. And so in this setting where we do have ancilla, and we're thinking of our quantum circuit as doing a computation, implementing a function on our inputs, we divide into two spaces, this set of computation inputs, which are then variable, and then this set of registers of so-called ancillae, which are fixed. And then at the end of the computation, we usually treat these outputs as junk, or maybe something that we'll do measurement on to induce essentially non-unitary dynamics in our main subsystem. From a more physics perspective, you can think of this as kind of creating a path that your main system would then interact with. All right, and then the last kind of key thing we need in order to define the QNC0 and QAC0 circuit classes is the relevant gates that will comprise these classes. So really, in order to define a natural analog of AC0, we need a quantum notion of an AND gate. It turns out that these AND gates also can then operate as OR gates, but just to define what these possible gates are, first we have the CZ gate, where essentially what this is doing is if the input to the gate is all ones, it'll apply a negative phase to your state and otherwise leave it unchanged. We also have a Toffoli gate, which is now going to have a set of control qubits and a target qubit. And if the control qubits are all one, then it'll apply a bit flip to the target qubit. Otherwise, it'll leave it unchanged. And then in describing QAC0's identity crisis, we'll need to define these notions of the parity and fan-out gate in the quantum setting. So quantum parity is kind of similar to the Toffoli gate. It basically is going to apply to our target qubit the parity function of the control qubits, therefore computing parity of all the bits into this one output bit. And just to say, there is a very simple implementation of this circuit if we're aligned for depth n, where you essentially take just 2 qubit versions of the Toffoli gate, known as C0 gates, and you apply them sequentially. This can also be simply reduced to log n depth by doing it in a more of a recursive fashion. And the key question is really whether or not we can implement parity in constant depth.
What is the relation between the Toffoli and the CZ gate in terms of AC simulate, AC0 simulate? Can they simulate each other?
Oh, so I guess this is kind of the key question we'll explore. So we'll see in just a bit. So the AC0 class will get the Toffoli gates. And the key question is then whether or not we can implement this.
But the ask between CZ and Toffoli.
Oh, sorry. So CZ and Toffoli, yes, are very closely related. You can actually get the Toffoli gate by just doing a Hadamard conjugation with single qubit gates on both sides. So we can think of CZs and Toffolis as really being equivalent in the QAC0 class. Okay, and then there is also this quantum fan-out gate, which is kind of an inverse of the Toffoli gate. So in the Toffoli gate, we had many controls conditioned on them all being one. We then apply a bit flip. The fan-out gate is kind of the opposite. It says condition on one control wire being one. We then apply fan-out to all of the other gates. So sometimes the Toffoli gate is referred to as a fan-in, and then fan-out is conceptually opposite. One very important thing to note in the quantum setting, and especially within this QAC0 circuit class that I'll introduce shortly, is that actually parity and fan-out are essentially equivalent. By simply doing a Hadamard conjugation of parity, we get the fan-out gate, or in this case, sorry, I'm conjugating fan-out to get parity, but the same also holds in the opposite directions. So this is a very interesting thing that happens in the quantum setting, where actually the two operations are in some sense equivalent. All right, and so with that, we can finally introduce our two main circuit classes of interest, which are QNC and QAC. So QNC is defined kind of analogously to the NC class, except in this case, we're given essentially arbitrary single qubit quantum gates. And then CZ or Toffoli gates of constant width. Once again, when we say QNC0, we're referring to a constant depth version of these circuits. And QAC0 is defined essentially the same as QNC0, with the key fundamental difference being that you can have these CZ or Toffoli gates operating on order n qubits. We also, again, have this important constraint, which is that the size is equal to the total number of gates, and in this case imposes a restriction on the total number of ancilla we can have, is a polynomial in the number of inputs. And so with that, we can now move on to the kind of main questions of this work and the talk, which is really understanding fan-out and parity in the classical and quantum settings. So we saw in the classical setting that parity and fan-out are not equivalent. And one easy way to argue this is in the AC0 circuit class, we get fan-out for free. We allowed in AC0 for the outputs of our gates to be input to multiple gates in the next level. But we saw by the work of LMN that parity is not in the AC0 circuit class.
This should be attributed to many other people before LMN.
Oh, yes.
LMN actually used this result.
Yes, yes, sorry. I guess it would be the switching lemma past that and over before. In the quantum setting, however, we just saw that parity is equivalent to fan-out. And so the key question for QAC0 is then whether both fan-out and parity are in QAC0 or outside of it. And so if it turns out that, so then there's two possible ways we could resolve this conjecture. In the first case, fan-out and parity are both in QAC0, which would then imply that QAC0 is much more powerful than AC0 because it not only contains fan-out, allowing it to simulate all of AC0, but then it also gets the parity operation, making it stronger than AC0. In the second case, if fan-out and parity are not in QAC0, then QAC0 and AC0 are incomparable from the perspective of the actual gates they can implement, because there are some classical gates which lie in AC0, which are not in QAC0 because of fan-out, but then QAC0 has all of these quantum operations it can do that AC0 can't, and we would need more of a decision style reasoning to argue about the relative complexity classes. So you might ask why we should care if QAC0 equals QAC0 with fan-out. There's a number of really cool implications if it turns out that these classes are equivalent, starting off with, as I mentioned, QAC0 being much stronger than AC0. But also then you get that, for example, QAC0 equals QACC0, which is essentially QAC0 with mod gates as well. And this is from a surprising result in the quantum setting that mod P equals mod Q, which is not true in the classical setting. We also have that QAC0 can generate maximal integral states. It can implement strong pseudo-randomness, which, for example, AC0 cannot implement pseudo-randomness. We also get a collapse of the quantum shallow depth hierarchy, where QNC0F equals QAC0F equals QTC0F. which again differs from the classical setting. And then we finally get that QAC0 is just extremely powerful. It can implement classical functions such as majority, threshold, arithmetic. In the quantum setting, it can do operations such as phase estimation and the quantum Fourier transform, which, for example, is an important subroutine in Shor's algorithm. So with all this background, I now want to move on to describing attempts trying to resolve this big open question.
So before the previous slide, what does it convince you that the answer is no?
Yeah, so I would say most of us believe that you should not be able to implement fan out in QAC0, and we're working to prove tight lower bounds. There is actually only one upper bound showing that fan out is not in QAC, or that fan out can be implemented in QAC0. This great work by Greg Rosenthal, where he showed that essentially you can implement parity and fan out in constant depth QAC if you allow for exponential ancilla. There is also work, I guess, or in the setting of classical AC0, you can also implement parity, I guess, if you make your circuit exponential size, because then you can just brute force implement any truth table of any Boolean function. But Greg's construction actually goes through a very different, more quantum route. It's really cool, but I won't have time to get into it in today's talk. One key thing to note, though, is that this is really far from being in QAC0 because, again, you have exponential ancilla, whereas QAC0 is constrained to polynomial size or many ancilla.
But it's,
is there an inherent barrier in improving this upper bound to sub-exponential?
Yeah, so right now in the quantum setting, we don't really have good techniques for proving circuit lower bound. So I'll now go into a discussion of lower bound that we worked on. Really, the main technique people have in the quantum setting is this notion of a light cone that we'll see in just a bit. So maybe I'll describe that and we can come back.
Oh, does the same upper bound hold for other functions like TC0 or AC0 you just mentioned?
Sorry, what?
Does the same upper bound hold for other functions like AC0 or TC0 you just mentioned?
For other, like,
what else can you do with exponential ancilla? Could you do majority, for example? This is your question, right?
Yeah, using this, could you get like some approximation to QTC0 or something?
Yeah, so I guess on the last slide, we saw that if QAC0 contains fan out, then QAC0 with fan out equals QTC0 with fan out. So then you get this kind of collapse of the whole hierarchy. So it should then become equivalent to QTC0. All right. And so now I'll describe some of my own work with Shivam, Natalie, and Henry on lower bounds for QAC0, specifically via this notion of Fourier concentration, similar to what we saw for LMN. And there's really two key results I'll describe now. So first, we show a parity not in QAC0 lower bound via a quantum analog of element. And we introduced a quantum notion of Fourier concentration for QAC0, which was a pretty nice structural result that then ended up having some consequences in different areas like learning theory. So as we saw, we framed LMN's result in the classical setting in terms of analysis of Boolean functions. So a natural way you might then try and move the LMN result to the quantum setting is through a notion of quantum analysis of Boolean functions. And so there was a proposal for this in 2008 by Montanar and Osborne, where they essentially observed that if you take a look at these so-called polystrings, which are tensor products of these I, X, Y, and Z poly matrices, then they have this key property that actually your polystrings form an orthonormal basis for complex valued matrices. And so what this means is for any, for example, quantum unitary, including unitaries implemented by the QAC0 circuit class, you can then perform a notion of a Fourier transform, where in this case, your polystrings are the orthonormal basis, and you have these U hat coefficients, which classically we would call Fourier coefficients. In the quantum setting, we like to call them poly coefficients. You can define the degree then of any of these polystrings as the number of non-identity terms. So essentially, wherever you have an identity, you could think of that as like excluding it from the subset on which it's acting non-trivially, in making the analogy to parity functions. And analogously to the classical setting, we again defined the polyweight at a given degree as the just sum of these poly coefficients squared at that degree level. However, then when we tried to use this notion of quantum analysis of Boolean functions in the quantum setting, we ran into a very simple roadblock early on. So in the classical setting, we saw that the degree of a Boolean function was a good proxy for its complexity. In particular, a higher degree corresponded to a higher complexity of functions we're computing. However, in the quantum setting, you can pretty easily see that actually unitary poly degree does not seem to indicate circuit complexity. So for example, if we take the simplest possible circuit in the QAC0 circuit class, where we're, for example, applying just single qubit X gates on every qubit, we have that our circuit depth is 1, but our poly degree is already n. So it's kind of concentrated at the maximal degree, and we can't distinguish it from, for example, parity or any high degree function. So this then led us to try and rethink the notion of quantum analysis of Boolean functions that would better capture the degree correspondence with complexity for analysis of QAC0. And in doing this, we had one kind of main key insight, which is that in the setting of, for example, AC0, typically when we're using these functions to do computation, they'll have a single output bit encoding, for example, the parity of the inputs. Meanwhile, in the quantum setting, these unitaries have many possible outputs. But since we're going to be using these unitaries to compute classical Boolean functions like parity, where at the end we'll only care about one specific output bit, this seems to be a bit of an unfair comparison. And instead, we should consider restricting just to a single output bit that's going to encode our computation.
But you can manipulate it by looking at the other outputs. Looking at the other output can manipulate the output that you want.
What do you mean by
measuring the other outputs?
Yes. So we'll see, though, however, that when we actually do this, there are some ways to get around that challenge. But yeah, that's a good point, and that's this problem with entanglement that arises in the quantum setting. So then in trying to define this kind of mathematically in a way that we can describe a notion of analysis of Boolean functions, your first question then might be, well, how are we going to restrict to a single output of an n-qubit unitary? And doing this is really just going to leverage this notion of a partial trace or discarding qubits that I mentioned earlier. And so now we're converting this unitary into a quantum channel, which is essentially this superoperator object where we're taking this partial trace after applying the unitary of interest to our initial state. However, this superoperator is a kind of complex functional. So then the question you might ask is, how can we actually then perform quantum analysis of Boolean functions on these quantum channels? And the way that we did this in our work was through this kind of clever math trick called the Choi-Milakowski isomorphism, which is pretty commonly used in the quantum setting, which then allows you to essentially embed a quantum channel into a quantum state. I think for the sake of time, I won't go into a full description of what exactly this mapping is, but the key thing to note is it essentially just takes your channel and maps it into a really large state, which encodes the action of the channel on all the basis elements. But I guess crucially, you then end up with this complex matrix on which you can do analysis of Boolean functions.
So what what will happen to parity when you apply this trick?
Right. So then in the parity setting, you'll get that, I guess, in half of it. So you'll essentially have, I guess, each of the basis computational elements. So you could think of these as being like x and x prime. Then it's going to be essentially entangled via this tensor product with the output of the channel on that basis element. So in this case, it's essentially going to be encoding the parity for that input bit. And so now you'll essentially be creating a state where you have all the different possible input combinations and this channel, the parity output corresponding to that input.
Go ahead. I mean, for parity, you get n classical bits, right? And you want the parity or exclusive order parity with another bit. So what happens to these classical inputs when you put them in this formulation? How is your new circuit going to compute parity? That's not clear to me.
Oh, so I guess this is now kind of a mathematical object that's encoding the parity function on it. And what you'll end up seeing is that even when we do this embedding, now this matrix, which is encoding parity, is still going to be high concentrated.
Yeah, I just don't understand the encoding that part.
Okay.
Yeah, but yeah, maybe anybody wants more elaboration or everybody's happy with this encoding of parity.
Like in your case, like the inputs, the possible inputs are ij, right? Like they're parameterized by a two-dimensional thing, not a one-dimensional thing. Yeah. Like I agree with Avi that it's not clear what is EU of the outer product of I and j. Like we understand that it needs to calculate, like it's very natural to give me a table that contains all the possible inputs, comma, all the possible outputs, right? And this is somehow a form of that, but maybe the output part is not clear.
So I guess in this case, U would be unitary encoding the like parity computation. So we saw, for example, when I was defining the notion of quantum parity, you could, for example, implement it in, say, logarithmic depth or in depth of n qubit with a fairly simple quantum circuit. So we do have like unitary description of the parity computation we're trying to perform. Then we're going to trace out all like n-1 of the bits. And so we're now just left with a single bit here that encodes the parity computation on this object.
So the 1 qubit part will be the parity of I bracket with parity of J. Is it?
Yes. And so what will actually end up happening for parity is that really it'll be encoded in kind of like a diagonal matrix, so that really ultimately we only care about the parity when these two are equivalent.
Oh.
So if the unitary U is a clean computation of parity, then the output 1 qubit will be the bracket of like parity I and parity J, is it?
So calling it a channel, it's another circuit, right? I mean, you call it a channel, But
Yeah, so when we do this mapping, the channel is actually mapped into a kind of a state where now the input is just entangled with the output of the computation. And so now it's going to be operating on n+1 qubits instead of just n, for example, in the case we have no n still n. Is that okay with folks?
Are we going to think about this as also implemented by circuit, or is this just existing in the world of math?
Yeah, so this is in our analysis largely a mathematical object. So it does correspond to a physical larger thing that you can implement in practice, which is given by taking the partial trace of the circuit. But like you essentially just create like a large Bell state, you input it to your circuit on one half, you leave the other half unchanged, and then you'll do a partial trace on the half where you're actually applying the unitary. So you could implement it in a lab setting. There's a bit of nuances with some of the normalization that we use in this Choy-Milankovsky isomorphism, but in practice, it is something you can implement in a lab.
the purpose of this is to create a quantum state from the parity function.
Yeah, so it's to, I guess, take this channel operation, which is more of like a functional, and map it into a matrix setting in which we can then use our poly decomposition to do analysis of the wave function. So it's a very different, I guess, approach from, for example, the classical setting to show low degree constant by the switching. So to then, I guess, prove low degree concentration, we just want to show that this, I guess, encoding of the channel, which in our case of interest is a channel corresponding to the parity function, is low degree concentrated. And our proof has kind of two main steps in which we do this.
Epsilon depends on case somehow and the size and everything.
Yes, yes. Sorry, I just wrote a small epsilon, but we'll have the theorem statement with the exact dependence.
And the size will also be.
Yes. And so the first step of the proof is we want to show that the weight depends on the number of qubits that the channel acts non-trivially on. And this is commonly known in the quantum setting as a light cone argument. It's kind of the main technique that we have for proving circuit lower bounds right now. But then really kind of the key thing that we use that allows us to surpass this kind of light cone barrier, which is the kind of main technique people use, is actually showing that removing large CZ or Toffoli gates doesn't really affect the average circuit output. So essentially it's saying that these really wide gates, which are kind of what distinguish, for example, QAC0 from QNC0, can be removed from the light cone with very little error. All right, so
just at a high level, what the result will show subsumes the classical AC0 lower bound. It implies them.
So it doesn't necessarily say anything, I guess, about AC0 because we don't have the fan out operation in QAC0. So you can't necessarily implement an AC0 circuit in QAC using QAC0 because of the lack of fan out.
So you somehow have a large fan-in using this Toffoli or whatever, but you don't have a large fan-out.
Exactly.
So it doesn't imply anything. So, although, yeah, I mean, it should, in fact, it should, but because AC0 or classical AC0 circuit of constant depth polynomial side, right? That will be formula.
Yeah, exactly.
And if it's formula, the fan out is 1. So why don't you prove a lower bound of classical AC0 then? Classical AC0 doesn't use fan out.
Yeah, you could always unroll it starting from the output gate and make a formula, which is like, like exponential in the depth. The depth is constant. Then.
But to do this kind of unrolling, don't you then need?
No, it's no, because constant depth. Constant depth is what any circuit of constant depth of polyside is also a formula of constant depth and polyside.
You change the variable set, right? That's the whole point. Maybe you change the variable set, like you add variables when you do this operation, right? I'm just checking that I understand. No, with the same
You
variable.
just unroll the circuit backwards starting from the output gate. You just enumerate all the possible paths from the output to like an input.
Yes.
And because it only has constant depth, there's only size to the depth.
Yeah.
Paths.
But you will make duplicate input bits, right? That's
There.
Yeah.
That's it. Yeah, you'll have
That's it. In the
Yes.
unitary evolution, it's opposite.
Yeah.
No cloning.
What was it?
Ah, kidding.
Yeah. Oh.
Yeah, and I guess that's kind of why we have this focus on the number of ancilla, because I think actually the better analog we've come to since this work is that the more natural analog is maybe classical reversible AC0, where then you have a restriction on maybe the number of copies, so like it's K copy reversible classical AC0. And yeah, I think might be an analogy breaks down. Okay, so as I mentioned, kind of a common technique for proving circuit lower bounds in the quantum setting is this notion of a light cone argument. And really all that's happening is we have this output of interest. We're going to throw away all the other qubits. And what we'll see is that actually the only inputs that can affect our outputs are ones that are either directly connected to an output or the output qubit or connected to it via a series of gates. And so then we can delete anything that kind of operates outside of this light cone. And what we'll see is that we have now only a restricted number of inputs are affecting our output. And so what we were able to show is that if for degree greater than the size of the light cone, the Fourier weight is equal to 0. So essentially what this is saying is we really only need to consider inputs which are in the light cone of our output. But I guess one of the key challenges, as we saw right in QAC0, is that our light cones, I guess, can be very large because our gates can act simultaneously on all the qubits. And so this really led us to our second part, which is trying to argue about the ability of removing these larger gates that really blow up the size of our light cones. And to do so, we kind of took some inspiration from this quantum analog of parseals, which essentially shows that for whatever object we're interested in studying, the Fourier decomposition of that object is related to the Frobenius norm, which is essentially an averaging over like the uniform distribution of classical inputs to our object of interest. And so one thing that you'll recall about this CZ gate that I mentioned earlier, right, is that it's kind of only doing something non-trivial if the input string is the all one string. Otherwise, it's going to leave our state completely unchanged. So conceptually, this is really saying our CZ only activates if all of the inputs are 1. And the probability of the inputs being all 1 with respect to this average case uniform distribution is 1/2 to the m, where m is the width, so it decays exponentially in the width of the gate. And so really what this is saying is that if we look at our object of interest from more of an average case norm, the Frobenius norm, then the closer, the larger the width of the gate, the closer the CZ gate is actually to an identity gate in norm distance. And so what this means is for wide enough gates, we can just replace the CZ with an identity or throw it out to very little average case error.
So this is just saying that from the, if you just want to approximate your function, and AC0 and NC0 are the same.
Yes, to some caveat in that we can't necessarily throw out gates of width larger than constant width. It ends up being like
Yeah.
gates of polylog width.
Yeah.
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 But
It's up to, yeah.
Yeah.
If you want polynomial smaller, you probably.
Yeah.
But that's it, so what you're saying, so it's independent of the final result. Any AC0, quantum AC0 circuit is equivalent up to tiny error one in polynomial to a quantum NC0.
Mhm.
Yeah. That simplifies math.
So what is A here?
oh, so A here is just like a generic complex valued matrix, like maybe unitary, maybe your choice state on which you're doing poly analysis.
Yeah, but why like the probability of X being or Y is 2 to the minus M? Like why can't this complex matrix A has all the values concentrated on this all ones case?
Oh, sorry. So I'm saying this is just a simple argument in the case that if this is a CZ gate, and you're now averaging over uniform distribution.
Oh, I see. So you assume like A is the uniform of maximum mixture.
Oh, sorry, this isn't a statement about A, but rather about inputs with respect to this Frobenius norm. Because you can think of it from a circuit perspective when we're taking the Frobenius norm, for example, of a unitary, that this is equivalent to running the circuit with different possible classical bit strings as input, and in this case, the uniform distribution over these classical input strings.
Yeah, I understand that, but I'm just wondering like this CZ gate will be buried in the like layer of the quantum circuit, and you are saying for any large CZ gate, no matter like where it appears, you can replace you can ignore it.
Yeah, and that's because of the unitary invariance of the Frobenius norm. So we can, I guess, like
Oh, I see.
analyze CZs that are buried within
I see.
via kind of like a hybrid style argument.
I see. Okay then.
But yeah, that's a good question, and it is a bit subtle.
So in this sense, you really need to go to the quantum channel if a QAC0 circuit is equivalent up to L 1 over poly to a QNC0 circuit. The single output will only see polylog number of inputs, of course, cannot compute back.
Yes. Yeah, so
So you need a quantum channel.
right, so I guess following this work, like there was a series of other works. So there was an improvement on Unbound by Anurag and some collaborators, Anurag Anshu, as well as like learning results that kind of leverage this. And instead of focusing on the channel perspective, you could look at it from the Heisenberg evolution of the measurement observable. And then you can look at kind of like the backwards light cone of that and prove that, yeah, when you measure a single qubit, the light cone or expansion of that is going to be basically a junta, and you get a very
So this
simple.
is it, okay.
Yeah.
Now I understand better what. I can understand the quantum channel, but maybe I don't need it.
Okay. Yeah.
Maybe some rough classical analogy to what's going on here, but the very rough is that like when you want to approximate, say, a DNF, right? You can remove like large clauses, like clauses with width greater than order log m, and like this is often done like in learning over uniform.
Assuming a uniform distribution.
Yeah, assuming
of
the uniform distribution.
This is something assumed here in this normality.
Yeah. I'm just saying it's a very rough analogy.
Yeah, no, it's a very good.
Yeah, but
That's, I was thinking this.
yeah, like it's like that.
Yeah, and I guess it's really this, okay, so maybe I'll skip here. I guess this is kind of just illustrating the light cone reduces to a Hunta light cone. And we get a precise bound on the error in terms of Frobenius norm. But then in terms of the main theorem statement, the kind of key way in which our argument or final result differs from that of LMN is that you have this S squared, but I think that might just be due to some looseness in some of our inequalities. I don't think it's like a fundamental thing, but you get this 2 to the A blow-up factor dependent on the number of ancilla. And this really intuitively is because of what Ryan was saying. For input qubits where we can kind of vary their value, we can do this average case argument. But ancillas are themselves like fixed input. And so we kind of have to assume that they're a worst case input, which then causes this blow up as we increase the size of our.
So this cannot handle more than polynomial number of ancilla.
Yeah, so I guess our explicit bound is like sublinear. There, as I mentioned, was work following this by Anurag Anshu at Harvard and a number of people at Peking University, which extended the result to slightly superlinear ancilla. And they did so using kind of a similar light cone style argument, but then they did some more sophisticated work using some Hamiltonian gap.
So why is K in this bound?
What?
You use K to be and to the 0.1/b.
The max value of K is N.
Yeah, I'm just wondering why you get N, the bound on the ancilla. I guess you
And that's why we think
K to be
remove anything.
in this bound, okay. But for polynomial size, it should be polynomial. If S is polynomial. Yeah, I don't know what, right? It doesn't seem slightly sublinear to me, it seems very sublinear.
Yeah, so I guess the size of the light cones themselves ends up being polylog size. But then in terms of the actual ancilla bound, it ends up being something. Okay. Oh, and I guess, yeah, we're hitting the hour now, so.
How much more do you need?
So I guess I can maybe just skip the discussion of applications that I was going to mention before.
Can you show the correlation?
Sorry.
Yeah. Okay.
So it's just saying when you have the sublinear number of ancilla, the correlation bound gives that this exponential decay, and so it's not much better than guessing.
And you mentioned that there is a row bound which allows more ancilla than linear.
Slightly superlinear, so it's like n to the 1 plus then small epsilon term which decays.
Doesn't matter, but somehow they can reduce it 2 to the 8 to something smaller.
Yeah, so they did so by using, I guess in part, a slightly more sophisticated technique. So as I said, we are in our proof approach, we basically said, we'll just replace CZs by identity gates. What they did instead was they replaced CZs by low degree operators, which then they were able to get much more explicit control over the errors. And they were able to get it to slightly improved value. They also were able to show that there's kind of a bootstrapping argument you could use where they have like n to the 1 plus epsilon, where then epsilon decays exponentially in the depth of the circuit. And they show that if you can remove this inverse exponential decay in the depth, that actually then you could use the bootstrapping argument to get the full proof for super polynomial ancilla.
Wait, like to actually show that parity is not in QAC0, you need how many ancilla? Polynomial, more than a polynomial? Like how?
Polynomial. So if
Oh,
you
no.
can rule out polynomial, then you've technically shown it's not in QAC0. But I think actually the belief is that really the tightest lower bound should be super polynomial, like on the end of being closer to exponential. So really
Yeah,
showing
okay, that would be like
construction.
a stronger even result, but
Yeah.
okay.
Yeah, but you only like to rule out polynomial, you only need to rule out like slightly super linear number of ancilla case.
Why?
This is because you like parity of
And
like you can do divide and conquer. Like parity of n bits is the parity of, let's say, root n parts, and they take a parity of the root n parts. Right? You partition it into root n parts, and separately you do parity, and in the end you combine them with a parity, and this allows you to bring, let's say, like n to the 100 ancilla down to like n to the 1.1 number of ancilla.
Yeah, but you need n to the 1.1. You really need super linear, but in the exponent.
yeah, okay, and then they have a decaying exponential, right? Like one plus epsilon over epsilon tends to 0. That's the problem. I'm trying to understand why they didn't get like that parity is not in QAC0. Using the divide and conquer, you actually need n to the 1 plus constant.
Yeah, or something that doesn't decay exponentially in the depth. That's like depth dependent decay.
I have a question. So I'm trying to digest what's going on here, right? You have like two techniques. One, you're really kind of counting the number of variables your output is dependent on. And the second is saying something about circuits that they really kind of vary. And both of these things are not quantum phenomena, right? Like, I mean, in the sense that at least in like the level that you've presented, it can be, you can say this about maybe classical circuits, maybe in an unnatural mode, but still. So kind of, is there something like inherently quantum in the argument that like I'm not saying it's like it's carried in this like conversion to the channel, or kind of is this just or are you really exploiting this kind of more deterministic part of the circuit?
I think this is a good question. I do think that there is implicitly some kind of correspondence with entanglement in the sense that these CZ gates are quantumly very weakly entangling gates. They, like from a physics perspective, have Schmidt rank 2, which is like the weakest type of entanglement you could generate with a gate. I actually personally believe that perhaps part of the reason we don't have a full lower bound yet is in part because of this reason. Like a lot of the techniques we've been trying to use to prove these results are fairly classical, and we haven't actually found very good ways of leveraging more quantum entanglement type perspectives in proving lower bounds. So I've been trying to play around with a bit more like entanglement inspired arguments, like physics style correlation based arguments, but it's pretty challenging. I will say, I think Honorog's approach that does get the slightly better bound. They do use a result from prior work on like Hamiltonian based approximations, things like that. So they are leveraging more fundamentally physics-based results and doing their like low degree approximation of this CZ operator. But yeah, it is a good point that this result is very classical looking, and I think that's in part because our goal setting out was to try and develop a quantum analog of the LMN result.
That's the reason I understood the result.
But still, it's not about exploiting it.
No,
It's about dealing with it. The fact that it's a quantum circuit, so it's a
Sure.
different
it's,
basis. And yeah, it looks.
I'm not saying that it's trivial or anything like this.
No. There's nothing to do with reality. It's a quantum argument, which looks very much like
Sure.
Yes.
Can you ask a similar question about reversible classical circuits with like some number of ancilla, like polynomial many? Like, do we know how to solve that version of the question?
Yeah, so this is something that we've actually been trying to look into a bit. I am under the impression that there isn't much on the classical reversible side, but I think actually from the perspective of helping in the quantum setting, proving like these sorts of structural results, like low degree concentration in the classical reversible setting would then be more directly helpful and analogous to what's going on in the quantum setting. Yeah, we haven't necessarily figured out a good way of reasoning about like a quantum switching lemma quite yet. So I think that's one of kind of the key barriers happening between the two, but there, to my knowledge, isn't really like a notion of switching lemma in the classical setting. So yeah. But yeah, I would say probably in the classical setting, then the number of copies you get of your input is kind of a direct analog of the number of ancilla you get in the classical or in the quantum setting. Yeah, and so I was just gonna have some discussion at the end about different applications to learning theory and pseudo-randomness. Maybe
Show them.
I can. I mean, instead of walking through them, I could show like a slide summarizing the high results, just to not keep everyone super long. And if anyone's like particularly interested, sorry, we'll skip through.
We
Missed a lot.
No, I think I definitely overestimated timing wise. So okay, so this is the summary talk. We spent time talking about structural properties of AC0 and QAC0, showing Fourier concentration of AC0. Sorry, this should be not element, but probably hostile. Switching. Sorry, this one.
Yeah.
All over bound. And then we have poly concentration of QAC0 with sublinear ancilla, which then explicitly rules out both fan out and parity in QAC0 with sublinear ancilla. So I then briefly mentioned at the start of the talk how LMN were able to use this low degree Fourier concentration to get a quasi-polynomial sample and time learning algorithm of AC0. Using our low degree poly concentration of QAC0, we were actually able to get an analogous quasi-polynomial sample learning algorithm of QAC0 with logarithmic ancilla. And this has to do with this fact that the support of the light cones is polylogarithmic. But there's actually a key interesting challenge, which kind of emerges in the quantum setting when you're working with these like channel encodings into states, which is that doing the projection onto the space of like these true channel encodings requires solving like an exponentially large semi-definite program. So actually in this case, the projection, which was fairly straightforward in the classical setting, becomes exponential runtime. And so Robert Huang and I did some work where we instead gave an efficient quasi-polynomial time learning algorithm for QAC0, where instead we actually learned the QAC0 unitary instead of the channel. And in doing that learning, we had to move away from this channel picture to these like Heisenberg evolved observables. And then in terms of randomness, I didn't have time to discuss it, but any AC0 function is distinguishable from random using a constant number of queries. And you can get this from like a sensitivity argument from LMN. There are other different possible ways of showing it, I'm sure, but essentially this says that pseudo-randomness does not lie in AC0 in the standard setting where you can use explicit queries. However, Katerinov in 1993 and then follow-up work by many others showed that you can use notions of shrunk PRFs, PRGs in AC0 to obtain computational or time-based learning lower bounds. And so we had a series, recent work with Ben Foxman, Natalie Parham, Henry Yuan, showing where that surprisingly we can actually implement pseudo-random functions, T-designs, and unitaries in QAC0. So kind of fundamentally different from the classical setting. And then using kind of shrunk down versions of these PRFs and PRUs to get computational learning lower bounds, which almost match the upper bound achieved in this previous work.
This is pseudo-randomness against what?
Against quantum adversaries.
So in the classical cases against classical AC0, well, there are PRGs against classical AC0 in AC0.
Sorry, not sorry, in the classical setting, it would be against like arbitrary computational adversary, not necessarily an AC0.
So the adversary in your case is also an arbitrary quantum circuit.
Yeah, and
So you have pseudo-randomness in QAC0 against any quantum circuit of ordinary size.
yeah, any, I guess, efficient time adversary.
Ordinary size, yeah.
And that's using.
But probably under assumptions, if you can prove that something cannot be done by any quantum precise circuit, you have the low bound for quantum precise circuit. You don't know.
Yeah, so.
What is the assumption?
So the key caveat, so we're able to in QAC0 with fan-out show that you can implement strong pseudo-randomness, and strong pseudo-randomness in the quantum setting means if I'm implementing some pseudo-random unitary U, then it's robust against adversaries that can query both U and U dagger. So the forward unitary and the back time reversed unitary. In the setting of QAC0 though, to kind of shrink down our QAC0 F constructions, we're only actually able to implement weak pseudo-randomness, where now you only get guarantees for against adversaries that can only query in the forward direction. And you can very easily show that they're not strong PRUs, like you could have a very efficient adversary that distinguishes those. So actually it does offer a path for proving QAC0 not equal to QAC0 with fan-out, in that we have strong PRUs in QAC0 with fan-out, weak PRUs in QAC0. So for example, you could show that QAC0 could never implement a strong PRU. That would give you the separation between QAC0 and QAC0 with fan-out. But a lot of this work on pseudo-randomness in the quantum setting is very recent. Like we use a construction by Mecker and all that was then proven to be produce strong PRUs by Fermi-Wa and Robert Wong just, I think, last year or the year before. So.
That's the last slide.
Yes.
All right, thank you.